I will be covering few things, high throughput screening, some case studies, and some bit of software stack development. So it's also, it's important that let's not do only applications, but we also develop something and give back to the community. So that's what this talk about. And then we will have, this Prince. This is the pre-science in silico solution suite, which we have developed in last 2 years during the COVID time. And we have released a version. This is a version 1. And after that, we have released a version 1.1. So this, some parts of the development, I'll also talk about the software. And also I will, you will get a chance to do a hands-on on this software. So what I have for you is a virtual desktop environment. So basically, like you are now logging into Exceed. Instead of that, you will be logging into our virtual servers and do use the software. But before we go in, to assign you the license and to assign you the VDI, we need some of the information. So if you see what I have done in the Slack channel, I have created a channel called Prince3 Demo. Okay, if you could get into the Prince3 Demo and subscribe to this channel. And then there is a Google form. If you could fill up the Google form, we need your name and email ID. Essentially, that's it. And once you get those, our team, Pre-Science, is following this Google form. So they will basically create a login and user and a password for the software to log in. So that will come at a later part. Means I will initially give you an introduction to the software, talk about it for first 45 minutes almost. So this company was started in 2019, and so it started by Jayant and me. Started at IIT Kanpur, Indian Institute of Technology, Kanpur. So in India, the IITs are quite well known, right? These are one of the premium institutes in India. And we are currently advised by few very nice gentlemen, and they are well reputed. And the new joinee is Sunil. He was a CEO of Titan Pharmaceutical. So it's a huge addition to our advisory board. So we are currently having 14-member team, and you will see that this out of this 14-member team, we basically are 4 developers, and how we have designed a software like this. So just to bring you to the speed of high throughput screening and what we are doing differently from any other software. So to go to that, I basically want to bring it to your notice is that this 99.9% early stage drug fails, and the drugs which are at a preclinical stage, 90% of the preclinical stage drugs that fail. That's a quite a lot, and it takes 14 years to get a drug approval. And then it takes almost like $2 billion for getting one drug from your chemistry lab to the bench, to bench to bed, what people generally say. So it's quite amazing story, right? And then we are computational biologists, we call ourselves, how we can help that journey to make faster. But what's the real problem, real challenge? The real challenge is scale. How, the scale of the problem is too large, simply because biology is too complex. It's very easy to say, pathway of some particular disease or things like that, but there are too many pathways for a particular disease. It's so complex. We don't know which is the proper target, unless you do a proper omics study. And that also is not 100% proven that all the omics is right and you have the real target there. Then the number of molecules to be tested, it can go beyond 10 to the power 60. So this 10 to the power 60 number is too large. If you think about number of planets and stars in the universe, that's around 10 to the power 60. That's the number. and we are looking for one drug from there for treating one disease, right? And the another fact is that the number of untreated disease still is 14,000, which is known to human, known to us. Is almost that we don't know more than 14,000 disease, which are, is there already in the world. So if you see the scale, if you see the scale is too high. So now, as I was telling you, the screening, the computational screening of drug or chemicals comes at a very early stage. And basically, you have these around 7 years of time frame, 5 to 7 years of time frame, which most probably we can control. And we can control how? If we can make this part more robust. So that is what our quest is, how you can make this part more robust, and as well as how many people can come into drug designing. And many universities, many people, many users put together their time and effort to make this computational science more profound so that we can quickly get into a drug or a useful drug, not only the science here. So, and then reduce the chemical synthesis, the number of chemical synthesis. If you can reduce the number of chemical synthesis, you can reduce the biology. And the idea is that you can reduce the scale at least by half. So you can reduce at least by 3 years. So that's the target. If you can reduce the time, the cost will be reduced. And the experimental trial and error, instead of 100 molecules to synthesize, if you can synthesize only 5, that also a huge achievement for us, particularly who are in this field for some time. So what we are proposing here from our company is that use of technology and technology of massive computing. So the proposal is that let's forget the legacy technologies and use as much as possible the modern technology. And why not? Because, we don't even understand when we are using technology using our mobile phone, right? Every day we are maybe doing some payments, doing some, food order. Everything is technology and it goes to cloud. If everybody can use a cloud, if everybody can use a massive computing, why not the computational biology people as well? So this is a tech-enabled tool. So what are the things we have done? We have done automation, good amount of automation, so that we can do things very quickly. We don't need to stuck on every step and check every step how it is going. Artificial intelligence, whenever we need that, as much as incorporation of that. And the new computing paradigm, which is cloud and high performance computing. So we have integrated cloud in the software in a way so that you can use the compute of, power of the cloud. Of course, you have to have money for using cloud, but it's available currently. And in the future tech is the quantum computing. Of course, we should not be forgetting physics for validation, because finally artificial intelligence might not be providing you the molecules which are correct, which are drug-like, or which has a very high selectivity. So to prove that or to validate that, you need to have physics, and you need to have a quantitative physics. You cannot do just simple physics or a qualitative physics and then leave 100 molecules at the bench of chemical chemists to synthesize that. So that's the idea. And then let's democratize. So make a software, give it to everyone. So now this is our platform, and this is a standard industry practice. So standard industry practice is that when you go for and buy some software from other vendors. So basically what you generally do, you screen, let's say 1,000 compounds. You have a team of chemists. They can take few of those compounds. They increase the library. Right? They just think that which library, what are the compounds will be better. They take those molecules, change the functional groups according to the pocket or on the docking site or the site of the binding, and they change it. So manually you can go up to 200, 300, something like that, right? Medicinal chemist, how much expanding of the chemical space they can do. Let's say we have a method, artificial intelligence method, which can expand the chemical space in an extra one order, right? We can go up to 1,000, 10,000 kind of a thing. So you are expanding the chemical space without the help of chemist, but we have enough chances to run it through checks and balances. So, and then we run it through checks and balances like synthesizability, drug likeness, and all these things. Finally, you can run it through our methodologies. And again, at any point of time, you can bring in a chemist to tell them that, ask them that whether it is synthesizable or not, this is good or bad. They can anytime come in and give you feedback. But we have this option of expanding the chemical space by few folds. Not only that, in the software, what we have done is that there is not only one target we are approaching, right? I'll give you an example of kinase. So if you are working on kinases, there are thousands and thousands of kinases. And experimentally, people do kinase assays, right? 4,000 kinase assay is quite common. Why? They're not only looking at a target, they're also looking at off targets. So the kinase molecule should work for a particular kinase for that disease. It should not go and bind to off targets, right? So you have to check at the same time whether it is specific to a particular target or not. So you have to reduce the number of off targets. So in this platform, not only one target, you can take hundreds of targets and run calculations. So that's what your high throughput comes in, right? It's multiple ligands and multiple targets. Then you can validate. So up to here, we can do docking, right? We have seen docking, how the docking is done. Docking is a method where solvent is not there. It's a method which is done on a free box, right? There is no solvent, it's a vacuum. However, the docking has a very high false positivity rate. And the false positivity, there are many reasons there are false positive numbers are coming out. One of the main reason is the solvent. So if you can treat the solvent explicitly, so that means if you can do molecular dynamics on the top, most probably those false positives can be reduced, the number can be reduced. Not only that, once you do molecular dynamics, you can expand that and do something like free energy calculations. So if you can get a delta G in solvent, then most probably you are reducing the number of false positive to a greater extent. So if you have these quantitative physics methods running, then most probably finally what you get, advanced compounds which are very less in number. Now you can ask me why, these are all well-known methods, why people are not doing it. It's mostly because of that we are still sitting on a legacy tech. We are not getting ready for taking advantage of the cloud as well as high performance computing in a way so that everybody can access it. There are a few groups in the world, they do it quite nicely. Few companies also do it, and then they get a success of it. What we have done, we put together all these things in a package, and we are basically giving it to the users. Chemical space, I have talked about. Yesterday, there were lectures where known chemical space is almost like 10 million known chemical space, although there's a claim of 2 billion known chemical space, but it's a claim. It's still not known that whether these molecules are really there or not. But 10 million is a kind of 10 to 20 million is a kind of known chemical space. We have to go beyond this chemical space, which it does, as well as it does new targets. So it opens up a possibility of not only the off target, it also opens up a possibility for repurposing. At the same time, why not we as a computational biologist that look into not only molecules for Alzheimer, at the same time we can look for molecules for let's say cancer, or if you are looking for a cancer target, let's say kinases, it might happen, whatever the molecular library I have made, this is most probably good, not good for the target, maybe a prostate cancer, but maybe very good for small cell lung cancer. So if we can plug in the pathways all together, we can screen much quickly. So it's a use of multi-target and scale your screening for multiple targets. So the diseases as well, off target plus multiple targets. Now, we have looked into this, the traditional approach yesterday quite a lot, that you have a compound library, you screen the library, you take compounds, almost like few thousand compounds you can take, you can do docking, and you can get 100 to 500 compounds from docking. So this is your traditional approach. What we have plugged in is a AI-generated compound library. So you can go beyond your number of compounds. You can add your compounds to this library. And then you can basically come up with docking again. And we have plugged in classical MD and enhanced sampling free energy methods, which is we are generally using a metadynamics method here, event-tempered metadynamics, which is state of the art, one of the best method. And then once you can do that, what you can do is that you can generate NCEs. So new chemical entity, as much as you can generate with confidence, you have the value of it, right? You have major amount of intellectual property being created. And you are contributing directly to the research of drug designing or drug discovery. So currently, I will be going through one by one all the softwares. So currently, we have 4 applications available on our platform. So I will talk about the platform a bit so that you understand this how the software stack is developed. So we have 4 applications: Chemin, BioIn, SciMog, and XESS. Chemin is basically, it goes and searches in ChemBL databases. So we are adding few more. We are adding Zinc, and we are also adding ChemSpider, but those are paid databases, so we need to still think how we can do that. BioIn is your protein modeling. So whatever protein cleaning and protein modeling is required, let's say if you do not have a structure, if you want to do a homology modeling, we still don't have the AlphaFold integrated. We are working on it. It will be done soon. And let's say if you are loop missing, if you want to delete some of the molecules or some of the chains, you can use this one to do that. SciMog AI is the app where we use graphical neural network to basically make the chemical space, large chemical space. And once you have the chemicals coming from either from Chemin or from SciMog, these chemicals, and here you have the proteins, the targets coming in. Once you have all these things, you plug into XESS. This is where MTML happens. This is where all the magic happens of screening one by one, docking, MD, and free energy. It happens in a scripted, fully scripted, automated way. So currently, we are in development of. This is the 2 things we are currently, focusing on: high throughput virtual screening, 1 million molecules onward. So we have just completed this one. We are now testing internally. Will be released by 15th of July. And we have an AI-based quantitative QSAR, which is again coming in another 2 to 3 months' time. So this is what we are adding to the software. So there will be 2 more apps added to this. And these are in the pipeline. Formulation screening is one of the pipeline. I have worked intensively in formulations, and that's a talk for another day. Okay, so future solution pipeline, we are also in some materials, and we are also looking at quantum computing. So offload some of the computation in quantum computers. So the key features, by now you have understood that the idea is that you have a pipeline, you have cloud integrated, high performance computer integrated, and you have a visualization, you have packages for Windows and Linux. Mac is currently not working because M1 has changed the total understanding of the Mac, and we are still not figuring out how to use M1. So we have a version for older Macs, Intel Macs. So, and then we have the fully automation integrated into it. So if you would like to see, I have kept some brochures at the back table, so you can pick it up. There are some brochures about the software is there. So this is the look. I will show you the software, so I'll run through the software. You can also test it, run it through. This is the look of the software. This is the first page. This is XESS, and this is SciMog. This is BioIn. This is Chemin. So I'll be running through some of the parts here. So the version 2 release date, 30th July. In the version 2, what we are adding is that blind docking. So you don't need to know the site of the docking. That is what we are adding. And then we are adding MMPBSA. People, users are keep asking for MMPBSA, so we have added MMPBSA as well. Then control systems. So you can use inputs from other softwares, like if you are using Schrodinger and you have docking done, you can use the input from Schrodinger. pH control, currently the systems are all at PS7, so we are basically using a pH control mechanism for doing docking as well as MD. And we are adding additional databases like ChemSpider and Zinc. Zinc, we are not very sure whether we will be able to do it or not, but ChemSpider we will do it, and Drug Bank we will be doing. Improved protein structure prediction, that is what we are also adding by AlphaFold. So now I'm coming to the development part of the software. Yeah. So this is a little bit heavy to understand, but please, stay with me. So what we are doing is a level 4 software. What do we mean by level 4? Is that we are trying to have a pipeline, and whereas these guys are not having pipeline, right? Means if you come to a commercial software like Schrodinger or something other than that, then you have to design your pipeline, how you want to go forward. Here it is pre-designed for you. It's the way we have designed, and most of the cases you have to follow the way. So it's a pre-design, and if you have any problem in that design, you can write to us. We have to redesign for something for you. So that's a level 4. So it's basically for simply for usefulness, so that anybody and everybody can use it. Then this is the platform architecture. I don't show it to everyone, so it's a little bit tricky. So we have interesting way to pack the whole software. So the way is that we have 4 things going on here. If you see this part, these are my OS level OS. Security software is embedded in the hardware, so security of the software is there. Then we have file system, automation scripts, and we have modules. All these modules, so this part is your OS, this part is the modules are packed into Docker. We are using Docker from last 2 days, right? Now you are familiar with what is Docker and container. So all the open sources are packed into Docker. So now these open sources are packed. Now what we are doing, we have something proprietary called data connector. So this data connector in the software, in our platform, it connects to your server where your Docker is running. This could be the same machine where your Docker, the same laptop where you are using the skin of the software, GUI of the software. Or it can be any other machine where you have the container running, Docker container running. So that means at the same time, this data connector is able to connect not only one machine, which is your local laptop, but also multiple machines, what is in your lab. It can connect to HPC, it can connect to the cloud as well. So basically this is the major part of our software, which helps to connect to the cloud interfaces. Currently, we are at Google Cloud. We are not at AWS. And we can also use our own cloud, which is hosted in Yota. Yota is one of the Indian cloud vendor. So you will be use OTA. The VDIs are at Yota. So now, if you see, then we are on the top, we are developing these apps. We call them applications or apps, like your mobile phone. And each of these applications does their thing to design a drug, right? It's a drug designing tool. So now, by doing so, what you are doing is that you are connecting, these apps are connecting to the server, sending the job calculations, bringing back the data after analysis is done. So, and then by doing so, this data connector keeps track of how many jobs it is sending, how many calculations are done, bringing back all the analysis data. So this is how the software interacts with your system in your in your lab. And this is very interesting because we generally do what? Say we have 5 people, 5 laptops are there. The laptops are not being used. All the laptops can become my crunching machine. It's not like that you need to have a fantastic server, to run your calculations. Okay, there are 5 group members, 5 machines are there. Everybody can run, all the machines can run calculations, or you can of course go to the cloud. Now, the stack-wise, that means if you see, we have client and server architecture. So client is your edge, server is your container. And then you have a data connector for connecting, sharing files with your client. And then cloud implementation for your accelerator. So in the cloud, we have implemented where we are using the accelerators like GPUs. You can also, so as a container, we have GPU containers, GPU-enabled containers, we have non-GPU containers. So if you see in our pre-science container, which is open source, by the way, if you know the, the path of the container, you can download the container. It's an open source container. We don't say that this is our container. We have just designed the container. That's it. Software is on our proprietary. So then application layers, we have AI/ML. We have physics-based methods. Currently, we have MD docking, free energy. Quantum is still not done properly. So we are planning to have NWKM in this. And then analysis scripts and the screening algorithms. And finally, we have visualization. Again, open source visualization is added to the software. So this is the architecture. I will upload the, the slides. Please have a look at your, that how we have done the architecture for client and edge, what is going, how it is done. Everything is, details is given here. This is the data connector, how this is, going to the Google Cloud, and authentication is done through our Django API server. So we have an API server. We basically, when you are hitting the cloud, we check whether we have given you permission to access the cloud or not. Then this goes to our server, checks the server whether you have the ability to do it. Then only it will allow you to access the cloud. Once you access the cloud, we keep a log. So that log is being charged. So if you are using for 10 hours, that will be charged in your next bill. So this is the cloud implementation, full implementation. As you see that we have these compute instances, which are GPU instances. And then this is the authenticator server, which is sitting in our server pool. In the Google Cloud, we have our own server pool where this app engine is running. In this app engine, we have basically API has been called to check whether you have the authentication to run in cloud or not. So, and the good thing is that you can also run it on cloud and on-prem. So you can do a hybrid as well. So you can go, few jobs can be on cloud, few jobs only in your on-prem as well. So application layer, we have artificial intelligence implemented, and we generally do graphical neural network. As you know that this is a very well known method currently in the literature, that you use basically junction tree, and with that we basically have this hierarchical graph encoder and decoder. So you basically encode your molecules, the training set, and let's say we have a training set for kinase. We have trained 30,000 molecules for kinase, and then we basically uploaded that model in the software. And then you are giving input, which molecules will be input for your GNN. And according to the input, this will be decoded. The input will be decoded, and the new molecules will be formed. Yes. Known inhibition, which shows good inhibition for kinase from ChemBL. We have currently six trained model in the software already available. So, and we are ready to do others as well. If somebody needs some other model, we can generate and give it to you. So, application layer, as I said, physics-based layers, docking, molecular dynamics, and free energy. So, molecular dynamics is run using GROMACS. Docking is run using Autodock. And enhanced sampling, that metadynamics is run using PlumeD. So if you ask me whether validated or not, so many papers are already there in the literature. It's I don't need to validate the software anymore. Yeah. Yes. This is PlumeD. Yeah. So these are all open sources. And if you don't want to use our package, you can use our Docker container, not a problem. That's for free. So yes. Mostly you have to run in GPU. From MD onwards, we don't tell to run it in CPU. To run it in GPU, say if you run 5 replicas of metadynamics, each replica would take like 5 hours, 6 hours in one machine, one GPU. So, and sometimes it is, if this is a very highly binding energy is higher, then replica takes longer. Higher means lower, binding energy is lower, means it's negatively higher, yeah. So we have already published few papers in this area. Please have a look at Laser that what we have published using this software. So the case study, I'll quickly run through 2 or 3 case studies here to show you that how the software is being used. So this is a case study for repurposing to treat cancer, customer project. Okay, though I am not showing the names of the molecules, these are kinases. So we basically had 4 proteins, 4 targets. These are all mutated proteins, so a set of mutated proteins. And then the idea was that 51 FDA drug they have given us to see which one is the best for these 4. So we have started with the docking. This is your 4, there are 4 lines. That means there are 4 proteins and there are 51 points for 51 docking. So these are 204 calculations we run. Then we have MD. So what we have done, the good energy is one we have taken, and then we have run MD. So MD we ran first 36 combinations because out of 204, we chose only to run only 36. This was already in full confidence. Then we have done MD. From MD, we have a scoring method. So we basically score as a function of, there are RMSD, from binding site, what is the distance of the ligand. If the ligand has already lost the pocket, it went to the solvent, then there's no meaning of doing it, because this is the solubility is higher. So those kind of things, we have 4 things currently, and energies as well. We are adding MMPBS, as I told you, that will be added to the screening function as well. And then we basically from there, we have taken all the 36 molecules combinations for free energy. And from free energy, if you see how we have, separated the energy. It's very interesting. In docking, if you see the energies are between, say, -11 to -9, you go to free energy, the energy separation increases heavily. It's because of the entropy and the solvation. So it's such an interesting see to look. In every project, we have seen that how these metadynamic simulations, free energy calculations or barriers can improve your results. So we basically came up with the best 5 drugs, gave it to them. They have a zebrafish model. They are now testing on zebrafish model. Once they test it, then basically, we know that whether it worked or not. Second one, so this is for COVID. In this case, what we have done is that in a very early stage in 2020, April, there's a Gordon et al. Paper, right? They have done a lot of proteomics, if you remember, proteomics on the host protein data, right? Host protein is that in a second stage, when virus is already at your body, in your body, then this is replications and translations are happening, right? Then how you can stop that replication and translation so that you are looking for drugs which can do that. So that was the study Gordon et al. Came up with. And they have proposed very good number of drugs and targets. We have taken 9 potential targets from them, 9 proteins, 12 binding sites. Few of the proteins, the binding sites were not known. So we have calculated from the blind docking. 28 drug compounds we have taken. We have done molecular dynamics, docking and the MD and metadynamics. So these are some results. So you see docking. So what I'm plotting is there, these are my proteins. These are my ligands, chemicals or compounds, known compounds. And then this is your, so darker the energy, darker the color, lower the energy, right? So we are plotting for docking, going to MD simulations and going to free energy. If you see from free energy, we can basically figure out that out of these pool of 28 drugs, few are very good to certain targets. And you see, this is a proper multi-target, multi-ligand approach, where the targets are coming from not only from translation, also from replication. So these are the target proteins. And we came up with these 4 molecules published initially in archive, even before the clinical trials started on these molecules. These are all in clinical trial. Chemostat has phased out. This is not happened. This is not work. Silmitasertib is still in the clinical trial in India. We might get the drug within a month or 2. The method we are using is fitting the space by ball. So, and then the calculation, the energy. So that has been now implemented in the software. So this is in the version 2 will be released. Now the SciMog, the AI application app, there is one example here I am trying to show you. So the challenge is, you have to get new compounds, right? We know that all the compounds are not that great, and we need more compounds because of many, different things. So there are large target space, disease space. Drug resistance is another problem. We need to have new molecules coming in. And drug selectivity, of course, is a major problem now currently. So if you can reduce the drug selectivity, then basically your toxicity goes really down for certain diseases. So the input is protein class, right? And then we have SMILE codes for, in this case study, for FDA approved drugs. So what we have done is that for, I think this was done for some cancer. I think it was done for prostate cancer. So you have taken molecules which are already approved for that from FDA or in the clinical studies. Those are my input. Then we have a trend model. As I told you, we have a trend model for kinase. We put in there. Then we basically came up with 5,000 new chemicals. We call it NCEs. And then from there, we did screening based on physicochemical properties, simple Lipinski rule, drug likeness, and not very fancy. And then once you have done with that, synthesizability scores, of course, then basically we ran it through our virtual screening platform, so this XESS platform. And then finally, we basically came up with few molecules which have been shown here. So this is still not been tested, not been published, just to show you that how this has happened. As I was telling you, we have 6 models already in the software. These are my FDA-approved drugs. These are my 500 generated molecules. Screening, ran it through, XESS and came up with the best 5. And these best 5 now, we are trying to see whether these are synthesizable, check with the medicinal chemist and all these things. Always the scores are not the best one to look for, right? So, okay, so I'm done with it. So I'll show you the software. Sorry. Yeah, sorry, this is for India, so students, I have this slide, sorry, I still have this slide. So anyone, if you guys are interested in internship, please, any one of you, please let us know. We'll be happy to, get you as an, and yeah. Master's thesis is an internship because we live on, if we have many interns, we have many projects running together. So that's okay. So any questions by now? So then if not, then I'll go for the, yeah. How? Yeah, failure. The thing is that unless we go and get a CRO to synthesize my molecules, test it in cell, at least in vitro, I am not 100% sure how much. But as per the literature and all, the metadynamics, if you go up to metadynamics, the compounds are coming out of that. You have the ADME. After that, you run your ADME properly. Then most probably the failure rate will be very, very low. I don't know this, means this is kind of a question we are still asking here. Yes. From that experience, that if you see, that COVID paper was a very good success because all the 4 molecules we predicted all went to clinical trial. Now, whether, you can say that, okay, there are so many drugs in clinical trial for COVID phase 1 and phase 2. Anybody coming up with something, they are going for clinical trial, right? So that's also Not every drug is there in the market. Still, we don't have antiviral, proper antiviral, other than Paxlovid, right? So, yeah, I would say that if we can get a cancer drug correct, or if you get a neurodegenerative or rare disease drug correct, I would say that it's a very good success. Yeah.
Okay, so my thing that I would like to see is that how do we tackle the multiple signaling mechanisms? For example, yes, I mean, whenever we talk about drugs and whenever we talk about screening, take one drug, one protein, many drugs, one protein. I mean, there are specific targets.
Yes.
From your software, could we get like a whole pathway?
Yeah, in the pathway, whichever protein you think is, I'll give you an example. We have just completed the work. It will be published soon on lymphatic malformation, LM, very well known rare disease. So we looked into the pathways and we find out there are at least 4 to 5 proteins to target. So AKT, PI3K, and there are 2 more. So 4 to 5 proteins to target. Not only that, the variants of the mutated protein. So like from the gene, what is the mutation, and then you mutate the protein accordingly. So it's around 10 proteins to target for that particular disease. So we just did a repurposing work for that on all 4 proteins with their mutations. And then we figured out which are the molecules will be good for that. Then we figured out that to our very surprise, that the molecule for this haldi, right? What is that name? Curcumin has come out with one of the hit. And so we looked into the literature back, and it is really been referred in the literature quite a lot for LM. So we were very happy that, okay, at least we got 5 drugs from that study. We ran around 50 FDA-approved kinases. And we were very happy to see that, okay, that at least we have figured out, which has been, proposed by people by assays, biochemical assays done, not, cell assays, biochemical assays done in a wet lab. So we were very happy that it came out, and very confident, right? 5 molecules. We didn't came out of 20 molecules out of 50. This was one of the best thing happens.
It was quite good. Now we have to use it and see that how.
Yes, I will show that then.
Yeah, there was one more question. The programs that you have shown us so far is the versions, like Gromax was 2018 version, Flumed was a bit earlier. So would you update them in your your pipeline?
Version 2 we are adding 2021. Currently it is running on 2018. Gromax 2018 currently running. We are adding 2021 in version 2. Version 2. So we are basically 3 to 4 months in a delay. Unless the versions are very stable, we don't put it in our Docker container. We don't update the container. And the container is, that's another good thing that we have a container. Yeah. Ish. Yes. Yes.
Then emphasizing synthesizability of the drugs.
Oh, after that, whatever molecules are coming out, we run through RDKit.
RDKit. Okay.
RDKit.
Yeah. So you're using pseudo retrosynthesis?
Yes.
Okay.
Yes.
You said you have 6 patent neural networks. All are GNN based or
all are
some
GNN.
others? GNN based.
All GNN. Yes.
Okay.
I have one question and then one comment.
Yeah.
The question is on the software side. Have you run it on the HPC?
Yes.
So how does the Docker permission, because Docker takes the root permission, how do you solve that?
Yeah, it's a very good question. Actually, we have a non-Docker version as well.
Oh, okay.
I'll show you that you can also in HPC, what we generally do, we have a full script which we run, and all through wget, we get it, run the script, install automatically. Paths are already, gets updated to our software. So you basically take the path, you put the path in the software so that you don't need to do a Docker. So HPC is, and then you can submit. Also, we have a submit script integrated in our software. You can change the, say, if you are using PBS Pro or Slurm or anything, you can integrate in our software the part of the PBS script. It will go and submit.
So the comment is actually for the participants. What he has done is raise the bar for all the graduate students. Because we would have done a little bit of part of that, design how to do free energy methods, or design how to do, develop. I have seen PhDs where they just develop the force field parameters to just run the MD simulation. Now with this software, you cannot get a PhD only by doing a little bit part of it. Because with such integration, the bar of the PhD student has been raised a lot. Thank you.
Yes. Yeah, so we, the company, we have is the main motto is that let's not reinvent the wheel. So if there is a wheel available, use it. So, and run your car. So that's what we always try to see. Whatever I have learned yesterday from this conference, I'll also try to see whether how much we can, take it, talk to Vish and talk to Amita and all. Okay, so I think that's let's see the last part of, okay, by the time this has been created, I'll show you the software. What I have is that I have 8 virtual desktop environments, 8 machines available. So as per the email, I get your email IDs. I'll create the license for every one of you. But the virtual desktop, you have to use it in groups. Basically, if the 20 people come in and ask, only 8 VDIs are available. So I can make them in the group and post it in the channel that, but this is the group 1, these are the people, this is the VDI. And I will share how to basically log into the VDI. For logging into the VDI, we have a method, which is this file. I will share this file with the groups. Every group will have a separate file because it has a unique ID and the password. Okay, so first thing you have to do for the VDI, you have to get a Citrix. This is a Citrix, and then you have to get the Citrix. Once you get the Citrix exe, you have to install that. Then you have to go and go to this web page. You have to add that Citrix desktop using the user ID and password. Not only that, it has a double authentication. You have to then install Google Authenticator on your mobile phone. And you have to add the Google Authenticator to the VDI. The VDI has to be added to the Google Authenticator. And then every time you log into the VDI, you have to check a code from Authenticator. Then only you can get into the VDI. Once you are in the VDI, then it's very simple. Software is already installed. Everything is already kept ready for you. Once you have all the user IDs and passwords has been ready, I'll club you up in 8 teams and share this document again on Slack. Slack, team, and I'll send this document, each of the teams document. So before going to this, by the time the team is now started creating the licenses, I will show you the software. So for the software, what we have generally do is that, if it is Linux or Windows, we generally go to My Documents, generally create 3 directories, okay? So if you see, there are 3 directories. One is IO. Oh, sorry, didn't share it.
have it. Thank you for your response.
Okay, I guess you can see it now, right? If you see, there are three directories. One is IO directory, one is Prince software directory. This is a software I have kept, and there is a project directory. So the IO directory is in the server side because all the server, whatever the server is reading and writing, it is happening in the IO directory. So don't touch the IO directory when you are, it is dedicated to the server, and that's the IO directory running. This after you create these three directories, then you basically have to start your Docker container. So to start the Docker container, this is the command. You have already run the command yesterday. I was looking into the Docker. So basically, sudo docker run --rm -it -GPU. This machine is a gaming machine. It has a, I think 3050 card, NVIDIA card. And then, this IO directory, you have to give the path of the IO directory. And this is the home ZAS, is the directory which is in the server. The server side, this directory is already there. So we have to map your local machine directory to the server directory. And currently what we are doing, you are using the same machine as server as well as my user, edge and server both. Then I am mapping to -P000. This is, I am saying that everybody can connect to it. All connections are accepted. Port 8080 and port 22 for SSH. Then I have this image name, this prescience / prince3 env_1_GPU. This is the name of the image, and the image is version 2. The tag is version 2. So this is the image which is stored in Docker. Once you release this command in your machine, it will take, let's say, around, as per your internet speed, it is the GPU Docker container is around 12 GB. It will download 12 GB image to your machine, unpack, and start the container. So I have the container already downloaded. So if I launch it, it will be launched, quickly. So you see, this is I am in the container. And in the container, you can, we are already in a Linux container. This is a Fedora Linux container. So you can do we have GMX 2018 installed. So you can, if you don't want software, if you want to run GMX, you can still run the Gromax, Docker, Autodoc, everything you can run from here. Now, once you are done with this, then we go back to our software directory. This is my IO directory. I go to the software directory. I was kept pinging because the internet was going. So this is my software directory. My software is in this directory, and I basically launch the software as a Linux command. Still we don't have the clickable thing. Okay, so this is the launch. This is the first page of the software. So now, I'll first show you the data connector. If you see, this is the data connector of the software. Here I have added the local host. What I have done, I basically have gone here, TCP/IP method, and from there I have decided to take the container type. So you see, there are three types. One is Docker environment, one is pre-configured, one is accelerated cloud instances. So Docker environment is that, let's say a server, currently this is my server. Let's say I want to run a Docker here also. In this machine, I have installed Docker and the image. I can pull this machine in this one and map it here as well. So that will be my Docker. If I want to have a pre-configured, that means I am doing an HPC. So I'll click here. You see, you have to give all the pre-configured libraries and everything. You have to give everything in this. And then if you go for cloud instances, you see already I have a cloud instance running here just to show you that cloud is running. You can call a cloud here. You can say, okay, I want to run one cloud instance or 10 cloud instance. You can put it here, you can say launch, it will launch the cloud instances. But if you have to first take the approval from us, because we have to add you as a cloud user. Currently, your passwords, what will come, there will be no cloud instances added to it. So if you are really interested to run in cloud, let us know. We can do something for you. Once you are done with this, then we basically go to local environment, local Docker environment. We map the IO directory. The input-output directory, we map it here, and then we save it. This is your setting is done. Once you're done with the setting, this setting stays in your software. Okay, so, and then once the setting is set in the software, and how I come to the software, I basically, I'll just show you the, so you can log out from here. And so first time when you log in, this is your page where your user ID and password is required, which will be given to you. Okay, so now we are ready for checking the software. So let's start with Kemin. Okay, so we basically generally start with like, launch the Kemin. So we basically say that, okay, Kemin, go to the directory. I am in the project directory. I can create a directory. First thing in this software is to create a directory for running a project. So any application you open, this is the first step. So I have created, I have opened it. You see the Kemin software is now open. And generally this is the left side is always an explorer. Below is always a log. And in between everything happens. So now I select a database. I can go for, KMBL database. I can select a protein. And I am looking for UniProt ID. So what it will do, it will give me for a particular UniProt ID, whatever the proteins are in that UniProt ID, for them, whatever registered molecules are there in KMBL, it will download all. So I have few projects been created for you. So this is like, this also I will be sharing with you. There are some projects are already created. So I'm going to use this UniProt ID. And go for search. So it is connected to KMBL. It's using the API of KMBL. And so you need an internet connection to run the software. Without internet connection, you cannot run it. Once I have you see there are, for this particular KMBL, the stress 70 protein, we have 41 associated compounds in KMBL. I can select them. There are some issues with the software, which I don't know why. Having. So you see there is now, you have this, all 41 molecules are coming from your KMBL. Now we have the KD values, delta G values here. If you have, you can also have IC50 values, EC50 values, as per in the KMBL, whatever people have deposited there. We can look for KD value. So you see KD value I am looking for, I just search for the KD. I can just, do a toggle here for the lowest KD values. These are my lowest KD values. I can take some of them for my next step. I can take them and check whether for this target, whether they are going to bind or not. I can go for SIMOG and all these things I can do from here. Or I can do a similarity search from here as well. So I can select all from here. I can unselect all from here. So I can just select all, and or I can just select few and basically go for say similarities, similar drug search. So similarity drug search is happening in Chembial only. So in Chembial only, these molecules have been run for the this similarity by this method. Is that you were talking about yesterday a lot? So, yes. So then we basically get the similar molecules from there, and then you can go ahead and do it. Instead of that, let's do synthesize molecules from AI tool. So I can, you see, I can click generate synthetics molecules from here. I can go directly to this tool. So no target bound. So it's not it's basically a ligand-based method, not a target-specific method. So you see all the 4 molecules smiles are now here in this AI app. And then we basically say, okay, I have the input molecules here. You can also give input from, you can manually give a smiles, or you can upload a canonical smile space for input, or you can also do it from PrintChem. So what we are doing is currently from in PrintChem. So now the models. As I told you, there are 7 models, 6 models are currently available. These are, let's say, use kinase model. You can go for kinase. And then we basically say that let's generate 5 molecules per input, or we can generate even 50 molecules per input. You can go up to 800 molecules per input. So it will take some time. I'm just showing you most probably 10 molecules per input to generate smiles. Okay, so you see this is my input upside, and on the bottom side we have all the outputs. We have generated 10 smiles per input, and we have also eliminated, if there is a the same smiles are generated twice, then basically we eliminate those smiles as well. So it's not always that you will get back 50. If you are asking too many, then maybe there are too many duplicates. Maybe you will get a reduced number of smiles here. And if you see that the synthesizability, log P solubility, all are being calculated using RTKit. So it's a very simple physicochemical property calculation from RTKit. We have here the filters. You can filter these molecules input and output as per your wish. You can also look at the properties visually. So you can select here, go, let's say synthesizability. You can see the distribution. This plot, the blue one is your input. This is your output of synthesizability score of the molecules what we get. You can look it into scatter plot as well. So similarity, similarly, you can look at the similarity, Tanimoto coefficient similarity, and we can go for a scaffold mapping as well. So as an input scaffold, how many molecules you get into the same scaffold type. So this also we generally show to the users as a function of input, as a function of output also. So this is generated smile, and this is a function of scaffold. So for this scaffold, these many molecules you got. For this scaffold, these many molecules you got. So by doing so, you are basically getting this molecule. Now this is the output here. What I can do, I can basically select some of the molecules from here. I am not using any filter currently. When you do the filtration, you can use any of the filters and see which drug likeness, which synthesizability you want to proceed. But I'm just randomly choosing first few, and I'm basically exporting them as a PDB structure. So this is if I hit PDB, so it will export all the smiles into PDB. We mostly use OpenBabel. So in our container, we also have OpenBabel. So whatever you have learned yesterday, you are seeing today a full application on a software GUI. So it takes some time because it's now converting one by one. Um, can you hear me? Yeah, now it is better. Yeah. So the K-mean, as I was telling you, that you can do also from, if you go back, see, if you don't have a UniProt ID, you can go for sequence. Here you can just paste the sequence, and then you can, run BLAST or FASTA. So from running BLAST and FASTA, it will look for similar proteins. I think we have a cutoff of 0.8 or something, and those associated compounds will be dumped to you. Okay, I'm closing this one as well. This is done. Now we have to now design the protein, right? That's for any. Now in this case, we will be designing only one protein, but in MTML you can do multiple proteins as well. So let's go to BioIn. Same starting point. You have to create a new folder. So let's call it Bio01. And you have to show the folder to the software. So now we are in this software. This is a BioIn. So if you see in the Explorer, we have the first part is editing the protein structure. Second part is modeling, the homology modeling. So we will do quickly something. We have the protein 6NHK. We'll go here. We will search from the database RSEB 6HNK. We are fetching the protein. So we got the protein very quickly. It's again, you need internet connection for running this. So if you can visualize the protein, and you can go for protein report. So this is just only one chain. You can check the ligand report that what are the ligands? There is no ligand associated with it. So I think I have chosen a very bad protein. I should have taken, so a very good protein. I should have taken something where the ligands and everything were there. But anyway, so there is nothing missing. Okay, that's good. We have some missing residues here. So we can at least model the missing residues. Secondary structure information you can get here. Disulfide bridge, if there is a disulfide bridge, you can get an information here. And then you basically go into the structure editor. We are using modeler. If you are non-academia, then you have to buy the license. It's in the Docker environment, so it's up to you. So if you are an industry, we basically tell you that you basically get the modeler. We can help you to get the modeler, not a problem. But academia is free. And the Docker container is independent. We don't claim that's ours. So now you see this is only one chain. If there are multiple chains, you could have seen the chains here. If there are ligands, you could have seen the ligands here popping up. And there are these delete buttons. You can delete everything one by one. And for this protein, we don't have, I haven't tested it. I'm seeing that this is a very simple one. So now basically we can delete water. The waters are deleted. And then I will go to the model refinement. So that means I want to do the modeling of the chains which are missing, right? The missing chains. So I keep this here, generate alignment. The simple modular steps have been incorporated here in a GUI so that you don't need to run, this. Not always. Some proteins we have problem, and but we are keep testing. We have a pool of around 600 proteins we are keep testing, and we are trying to address as much as possible issues. At least we are trying to give the error message to the user. If it is not possible, user should know, okay, this is not possible with this software. That is what we are trying. Fail-safe. We are now currently working on fail-safe of the software. So basically, this is the alignment. It gives emboss alignment, and you will see the missing residues have been given. We say that, okay, this is a good template. Let's go ahead, and basically that will generate the starting loop. If I keep it here, can you hear me also? Okay, great. And one hand is free. Yeah. So we have now, I guess this was the missing part. Now we can go for the loopy, proceed to the loop refinement. So we have to now energy minimize the loop, what is been predicted. So we can go there. This is the loop which was missing. So these are the like 26, 27, 28. These are the residue numbers which were missing. We can generate up to 5 models. For the time, let's generate only 3, and we can say refined model. So now these 3 models will be taken up as the initial, and then it will be, the dope scores will be generated for that. So if you see, we'll come to get a dope score here for 3 models for this loop. There are also many features in in as well as in. I have just shown you a little bit the main thing, but there are things which are hidden. You see now we have the 3 loops. The one here, there is one here, and there is a one here. There are 3 loops, and we can look at the dope score and take the lowest score. So this is -851 is the lowest score. Let's go ahead with the number 1. This one. So now we can go for the next step, which is either we can go for point mutation. So if you want to mutate the protein, which most probably you have to do if you are working on multi-target environment, you might want to use multiple mutations and then run your screening. In this case, we are not doing it. We just run one protein at a time. So then we can go to the structure patcher. In structure patcher, we know that we have to take the number 1. Number 1 was the best score. And we just add missing hydrogens to it. right? And side chains, whatever is missing, we just add to it. And once it is done, we just, we are done with it, and we can save the protein. In some cases, the software stops here as well. Then basically, it will not generate the structure. Some cases, then we have to do some manual intervention. Sometimes it happens that. So we have done it successfully, and then you see there is missing atoms added. Always look for the log, what is happening. So log is very useful to see whether it has happened or not. Export PDB. Now we can go to projects. We have ligand. Let's create another directory here called protein. Yet. And then say the PDB file name, it was 6 NHK. Okay, let's say refined. Okay, the file is now saved in the protein directory. So, documents. Yeah, we have the protein file. So now we see we have ligands coming from synthetic molecular generator, and we have protein coming from BioIn. And the last step is to go for screening. So this is the last app, the XCSS. We open it, same procedure. We go for projects. We create a new directory. Let's call it, ESSS 01. We create it. We open it. There is a project. Projects open. Now you see browse target structures. Here you can browse a directory, not the protein. So in that directory, I have only one protein. I could have kept 20 proteins there. All will be read. All will be taken in the platform. So that's why it's a multi-target environment. So I have only one, but I still, we have to do the same procedure also for one. The protein, open. You see only one. If you would have many, it will show you the many proteins here. Okay. We will browse the ligand structures. We go to the ligands, and we just browse it. All the ligands will be read to this one. You see all these, I think around 6 or 7 ligands have been read here. So now, okay. So we have now all the ligands and everything is here. So we can click here and we can see the ligands also. You can click the protein and we can see the protein here as well. So ligands also, you can have a look here, in this case. So now we can just go for proceed to docking. So it is basically, will take some time for preparing the PDB-QT files and all these things. It will take some amount of time to get into the stage. Generally speaking, if you are running 100 combinations, here in this stage, you have to wait for 30 minutes. So if you are very impatient that, okay, I have 100 combinations, but this quickly done, no, it's not like that. It has a preparation steps, all been taken care at the back end. So here you basically will see the symbols rolling 100 combinations, 30 minutes. If you have 500 combinations, you might need to wait for 2 hours at this step. But once these steps are all done, then your docking calculations will be also another add-on. So we have tested that how much we are doing, how good we are doing with the numbers. We do pretty good. Up to 500, 600 combinations of docking is very well proceeded in this one. And if you want to do much more, say a scale of million, then I recommend you for the HTVS package, which is coming in another 1.5 months. So that's also, that you can do a million very quickly. You see now we are ready at this stage. So it took you around 2 minutes to come to here. Now residue numbers, we have to give the residue numbers here. So I have the residue numbers already, binding site residue numbers. So you see the grid is now shown. You can change the residue number, you can change the grid points, but it is fixed. If you are doing multi-target, these grid points and everything will be fixed for all the targets. And it is expected because maybe you are doing only kinases, or if you are doing family of kinases together, you are not doing kinase and a transporter. So it is expected that your mostly the grid points and everything will be somehow very similar. In the advanced docking setting, you are, population size, energy evaluations, and number of GA runs. It is running LGA. So I'm just changing to 10 so that quickly we can run it, all the calculations. Then, okay. Sorry? Yes. That is okay. Fine. So now you see you have this, and basically that's it. Means we just now go and run docking. So you have combinations. You see here protein name and the ligand name is taken. If you had 2 proteins and the same 6 ligands, you would have 12 combinations. So all cross combinations have been considered as well. That is the most interesting part. So if you have 10 multiplied by 10, you have 100 combinations been taken. Now you can select, okay, I don't want to run all the combinations. These are most probably not required for me. You can select which combinations you want to run. You can select those, and let's select all of them. Goes here. Now you have a local host and the cloud. So I can choose local host here. Cloud I don't want to run because the cloud is a GPU cloud. Autodock doesn't scale in GPU. So I'm just running in the local host. And sorry? Is it? Okay. New Autodock Vina, okay. This is Autodock 4. The 4. Okay. So start docking. Yes. So you see there are, and also it shows the total time take for preparation is how many minutes, how many seconds. You can estimate that, okay, you have 500 combinations, how much time it will take. So this is the final sheet. It will be loaded very slowly, quickly, that all the jobs, what is running at your server side. Yes. Who you are? Hit the table. The error. You take another. Then this, but then what I will do, I will show you download the software where actually, okay, by the time it is loading, what I can show you is the let's see. 16. Okay, it is still loading. So let me show you this. This is our web page. And if you go to the product section here, so you will see the user login here. So this user login will be your email IDs first, the username. You can log in with that. The password I will share with you. Everybody will have the same password. And then if you log in here, you get into something called user dashboard. So this is a user dashboard. And in the dashboard, you will see the license. So you see the license info. So till, which date you have the license, how many machines are allowed for your license, how many machines are currently active. I have 8 machines are active currently. And then if you have a Google account activated or not, if you have a Google Cloud, here you will see the allowed instances. Currently, I have active instance 1. One instance is running. I have seen that. So now, this is you will see. And then you can go to the installation. So this is the installation manual. Not very well written. It's a little bit messy. So if you have any issues, just drop me a mail. I will get someone to help you in installing this. Okay, so, and then basically the installer is here. We are trying to freshen it up. We are refreshing the installation method. So this is the installer. You can get the installer and then installation can be done quickly. But the installation is messy just because that you have to install Docker, you have to pull the image, you have to map the image, and then you have to start the method, right? So it is a little bit messy. Then you have the documentations as well. So you have the manuals here. So all the 4 application manuals are here. And the case studies are also, some case studies are here, but I will be sharing the case study document, what I was showing you in Slack right away. And then you can do those case studies as well. So here are some case studies given here. And then if you have any issues, also you can push a ticket, means you can raise a ticket from here. I think you will have the license active till a month. Full month you will have the license active, you can test it anytime. Any issues, let us know. We will be happy to help in that. So yeah, this is, you see, by the time we were talking, this is loaded, and then some calculations are also completed. See, there are 7 calculations are happening. These are the combinations. This is the allocated server. There is currently no error. Download status is down, download completed. So if you are running 500 combinations, you will see the 500 lines here, which calculations are running and where the calculations are running. If you added many servers, you will see the locations of the many server. You can refresh it from here and keep checking that what is the status. And if you are Linux nerd, maybe then you can also do a top, and check it whether something is running, Autodoc is running or not. So currently this will do the analysis because we also have some analysis here, and it will show you some plots. And then from here, we'll proceed to molecular dynamics. So it's quite good that what I generally do before dinner, I basically put it up. Next day morning, if I'm running 500 combinations, all are done in next day morning. So I just leave the computer on, and all done. Huh? Yes, this laptop only. Sometimes we hook two laptops together. So the same network, if you have 2-3 network laptops, you can just hook it, get maximum power, and then through. In this laptop, we have ran even molecular dynamics and free energy calculations for multiple combinations because there is no time waste, right? It just goes on. So, okay, so you are already ready with the software. Software accounts are ready for all of you. So I'll just show you a bit around how to get into the virtual desktop VDIs. So I'm doing a stop share here. Go for here. Okay, so this is the VDI to launch, right? So log in into the following. So we are basically going to log into this this web page. This is the step 3. Step 1 and 2 is to get your Citrix and then add into the Google Authenticator. So I will be sharing this as well. So here you can go to this. Here it will ask you for the user ID and password. This I will be providing for 8 such machines. And I'll have to look for the passcode. So this is the authenticator, Google Authenticator. So Yes, no, it's a Google Authenticator. Oh no, some issues. You will land into this kind of page. Once you open it, you will see this kind of page. And if you click to this, then your Citrix should show up. Sometimes it creates some issues. I don't know why, but it should work. If it doesn't, then let us know. We have to tell the IOTA people, means the people from whom we have taken this, they have to fix it. Okay, by the time it comes up, maybe we can see where are our calculations. So we can refresh again and see the status. Yeah. So you can view the analysis now. You can go to next here, and you see this is the docking energy for all the drugs. And I can go, the energies are not very good, right? -7, -6 or something like that. You can check the docking score as well. You can check the histogram, that how there are 10 GRONs. You can see the histogram. Then you can see the best dock pose. The molecule is almost outside the pocket. It's not even gone in. Same here. Then you can look for interaction views. So a closer view with your, hydrogen bonds are denoted, at which hydrogen bonds are, or covalent bonds, van der Waals interactions are there. And after that, you can go to the MD. So in MD, this is the stage where you can decide which combinations you want to take it for MD. You can decide and take it all of them, by setting the cutoff as 0. You can decide that energy-wise how much cutoff you want to take, and then you can take some of the combinations. So let's say we have seen that there is around -6. We can set it up. Then, or we can go a little bit more, 7, only 1. I'm taking a little bit more because there is a reason for that. We'll see that what is the reason. Then we are in the first page of molecular dynamics simulations. See, molecular dynamics simulation, the first thing is that you have to generate the force fields. And that is the major bottleneck for not doing MD. So here you can have, we generally use Lickpurgen and Swiss param. So this software will guide you to their servers, to the external servers for generating the force fields, or you can manually upload. You can prepare your own force field and manually upload in Chromax format. So you see, this is showing some, please correct it before processing further. So we are not taking responsibility of your force fields. So now you see we have 3 molecules, unique molecules, 0, 3, 1, and 2, and 6. So these are my ligands. I have to generate force fields for these molecules. How I'm going to do it? We can select, let's say, switch param, and then download the 0 ligand. So download, when I say download, what it will do, it will give you a mol file. And it will also direct you to say, here I can say, I can create another folder. Let's do it again. Download, create a folder. Let's say we can name this, okay, already this is downloaded in this folder only, so let's not create again. So cancel folder, just name it MEFF, create, open. And now we can browse that mol file. And submit. Let's see, means some cases, Swiss param could not find force fields. In those cases, we are, you are helpless. Basically, you need to know how to generate the force fields. And if you have issues, you can let us know. We can manually generate and give it to you. So that's another possibility. But those cases, the users are mostly helpless here because this is a new ligand completely, coming out of AI tool. So it might happen that you don't have the force fields ready. Yeah, we got the force field. You see, this is a zip file. So what we'll do, we can download the file. And then go for the another one. Number 3. Download. Same method. So one by one, we will do it. We will upload and browse. Number 3, open, submit. It takes few seconds, almost a minute, to generate the force field in this Swiss param server. We have talked about it in the morning, right? The Swiss param leak purgeon server. So this is what we are using currently. There is a one tool we are developing currently for automating the whole force field generation from our side as well. Okay, this is also generated. We are quite lucky today. Okay, I think let's proceed only with 2. We can go back and decide on 0, 0 and 3. Okay, proceed. Okay, so now we have 0 and 3. We can show the file folder for the zip folder. So that was in download. We have the 0. Open. Then we have 3. open, upload. So now the force fields are uploaded. We are ready to go for. So you see the Swiss param charm. Force field for protein is also charm. Water, you can choose whichever model you want to use. Let's say we are using TIP3P. And then you can go to the next. So here we do 3 steps. We do energy minimization, NVT simulations, and then NPT simulations. So for energy minimization, these are the steps. You can go to the parameters here. So this is the number of steps. This is default. You can go for advanced parameters for MD. You see MD, all the parameters are there. You can choose, change, whatever you want. Everything is given. Everything is outside, user controlled. So NVT simulations, we can run it a little slower. And NPT simulations, we can go for 0.5 nanoseconds. Okay. And then update. Then go to next. And you see there are only one protein. There is only one APO simulations will be done. And the 2 ligand simulations will be done. All these 3 simulations will be done. So select combinations. All are selected. I can go for both the machines here. This local machine should have shown me a GPU. I think there are some issue we have missed somewhere. The GPU here. Should not be 11. Should be, I think, 6. The number of threads are 6 in this machine. This is an i5 machine. It's 8 actually. I have taken only 6. And GPU, I said yes. So it's taken up. The GPU should be taken here. Yeah, you got the GPU button here. It's a CPU, GPU, where I'm using cloud as well. And why the run button is not activated? The cloud not working. So it's going to take around 8 hours for these 2 calculations. It overestimates. It will be done in more or less 2 to 3 hours. So you can just submit it and let it run. So this is mostly that. After this, the free energy is there. So again, you have to decide on the parameters, and then free energy you can run. For all these combinations, you can run the free energy. And you can choose the number of replicas also in free energy. So this is almost all about the software. Now I have to see how I can give it to you so that you can use it. Now that is the last bit of it. Any questions till now? Yeah. The manual, in the manual, the case studies are tutorials. I've shown you the software manual, right? And these are also tutorials, right? This is like, you can take which protein, why this protein, that there is a description is there. These are the only inputs you required. Other than that, you can do that. And the manual is, you can go to the, installation, the documentation. And if you go to the case studies, it's a well-written case studies are there. Say this is a searching of FDA-approved antiviral COVID-19 using multi-targeting approach for multi-scoring approach. So you can click here, download, and there's a zip file gets downloaded, and in the zip file, you will basically see the case study. And in the case study, all the input files required for all this free app as well as a PDF. Full tutorial is here. Okay, so you can basically, once you get a hold of the software, you can try out things. Okay. Lipid. I'm not sure whether it will work or not. I haven't tried it. Means if it is a membrane protein, then membrane bound protein, then it might work. I'm not sure. We have to see whether it works or not. Might work. In the free energy method, the parameters, for metadynamics, the Gaussian parameters you can define. We have default parameters available, mostly works for small molecules. But if you, let's say, if you have a larger molecule, let's say almost 600, 700 gram per mole, then most probably those parameters you have to tune a bit. But those are outside to the user. User can change the Gaussian, how much tempering they want to do, they can change it. So, yeah, you see, this is started running. It's a 1.2 is nanometer for from the protein side to that. So it goes pretty big. Basically, some big proteins we have seen that the total simulation box goes around 4 to 5 lakhs, almost 500,000 particles. All those are managed. Salt concentration currently user cannot change it. It's a pH 7. So if there is negative charges, all the negative charges are adjusted by counter ions currently. But we are taking that out also. In the version 2, that will be given to the user so that they can also adjust it. Initially, our idea was to basically thought that it will be a completely closed black box. Then we are slowly now seeing that the users are interested to change some parameters, and then we are taking those out. pH also, we have now a very nice algorithm to basically solving a proper pK equation, and then at that pH, which amino acids has to be protonated or deprotonated. Those algorithms we are now adding to this, so that this is well taken care in the docking as well as in the MD. Yes. Pressure coupling, you can use anything you want. This is a parameter you can change. You have Nose Hoover, you have Karparino Lehman, and also you have V-Rescale and you have Berenson. All are given to the user. The advanced parameter section, everything is there. Even the integrator is outside. You can choose the integrator. No, it's a single sign step. In Gromax, it's a single sign step. Yeah. Also, it's in the hands of user. They can choose 0.1 or 0.2. So the 1 femtosecond or 2 femtosecond, whatever they want to use. Sorry. No, you cannot. No. For all atomistic, you should not. No. I will. Yes. Gromax doesn't have that. That is most probably Amber's. Amber is much faster because of that. I think but if you are running in 1 femtosecond, 2 femtosecond, Amber is not probably that faster. I don't know, most probably I have bored the audience to the death. I mean, it's like, no, I'm not waiting for this to finish. It's not to, I just want to now, basically what I'll do, I'll stop the session and I have the email IDs already. In Slack, I'll be posting these groups. There are 16 email IDs, so there will be 8 groups. I will be posting each group. I will be giving you one VDI. VDI cannot be used concurrently. So you have to use, take a turn, or you have to sit together and use the software. And also you can log into the user dashboard. I showed you the user dashboard, and you can download the software, download the Docker container, use your laptop as well for testing. So for doing an evaluation, so that's possible. So this I will now pass on to you. The session is over, so that's why I'm asking that if there is any questions. So VDIs are working. If you see, if I have loaded a VDI here. So this is, you see, this is in my Mac. I have a Linux VDI. And the software is, if you do a ls, I don't know why this is so laggy. Yeah, it is working. So if you do ls, you will see there's a document folder. So in the document folder, you have IO directory, you have this prints directory. So in the prints directory, you have the software. So if you go to this prints directory, you will see the package here. So this is again a directory. So, and you can launch it from, so if you press PR and tab, you can launch it from here. It will be a little laggy because this is a VDI running on shared codes. It's not a full core we are using. So this is, you see, you can log in. And generally what you will see, I will log out and you will see this window first. So you have to put your email ID. Password I will be sharing with you in Slack. You can give your password, then your software is running. One thing you please remember to, before you start it, you have to launch this command for Docker container. So the command is this one. Okay. So this also I will pass on in Slack. And the command is already there. You can do a Control R and then you can get the Docker and then you will get the command. So if you launch it, then basically you are okay. The container is already running, so it's already, that's why it's located. So you can do a Docker PS. Yeah, container is already running here. So this is what it is. If you have any other questions, I'll be happy to answer. Otherwise, rest of the things I will be instructing in Slack.